So this video is going to kind of go over the differences between the standard normal or the Z tables and our new distribution we'll be talking about, which is the student T distribution. So the student T distribution, we're going to calculate, if we try to calculate our Z score, right, we don't have the population variance. All we're going to have is, all we're able to observe is the sample variance. So we're going to approximate what we would usually do to calculate the Z score, but instead we'll use a sample variance we get from the sample as opposed to a population variance that's told to us. So instead of Z scores, we end up calling these our T values or T scores. Okay? So we knew that Z scores would follow a standard normal distribution. The problem is with T scores or T values, they won't quite follow a standard normal distribution because we're approximating the population variance with our sample variance. And remember, if we go back, the sample variance we were dividing by n-1. So our approximation will be off depending on the sample size. If I divide by, 2 instead of 3, that's going to cause much bigger differences than if I divide by 999 instead of 1,000, right? Just kind of thinking about the -1 difference there. So what ends up being true is we actually have a different student T distribution at every single sample size. So we'll just think about what that would look like for one sample size. So let's say, n is equal to 50, perhaps. We use our sample variance to, it's the best guess that we have about what the population variance is, and we turn different values into these T values. Well, those T values would have a distribution that's slightly different than the standard normal. And the difference is going to be is that it's a little bit more spread out. Right? So when we divide by that n-1, we get a slightly higher variance than if we were able to actually observe the population data and only divide by n. And so we're always going to end up with, remember what kind of is in our denominator, this represents a standard deviation for our sample means. It's just now this indicates I'm only using a sample variance to determine that. So this is going to be a little bit higher, which means my distribution is going to be a little bit more spread out. So when I turn these into T values, what's going to happen is those T values will have what looks like it's a normal distribution. Sorry for my drawing, it's a little bad here. And it's still going to be centered around the same value, right? The population mean. So when we turn the population mean into a Z or a T value, it'll still be 0. But with this student T distribution, you can kind of see if I wanted that same area of 0.025 in this left tail, well, now if I keep using that same value that I would have used for the Z distribution or the standard normal distribution, that area is going to be much larger. So what has to be true in order for me to get 0.025 in that upper right tail here is instead of using 1.96, I'm going to have to use a T value that's something higher than that. So when we look at kind of these values to build confidence intervals, right, that we were using before, that gives us alpha over 2 in each tail. Well, now the value that gives us alpha over 2 in each tail, if we compared that to the value that would give us alpha over 2 from a standard normal distribution, the T value that gives us alpha over 2 is going to be something that's larger. So because of this, when we try to build our confidence interval, we're going to have to use a different table. Essentially, there's a different probability density function that's floating around in the back. We don't want to integrate it. Someone else already has done this for us. So we have a new table that we can use. And this value will depend on what that sample size was, because that sample size is what was causing the difference between our sample and population variance and the difference between the distribution of our Z versus our T values.